At the top, let's draw our pendulum. Okay, swinging backwards and forwards. All right. And what I'm going to try and do is draw a graph of displacement against time. And this is the bit you need to be prepared for. Underneath that graph, but lined up with it, I'm going to draw a graph of velocity or speed against time. And underneath that one, I'm going to draw a graph of acceleration. Any moving object, and this is one of the most complicated motions that you study at A-level. Basically, if you know where it is, how fast it's moving, and what its acceleration is, then that's it, all right? If we can draw these three graphs and understand where they come from, then we should be okay. Okay, let's take the first graph then. I'm going to be a bit strange because I want to start my graph here. I want to start here. First point there. Why is that a bit odd? Whereabouts in the swing is that? You normally start pendulums from the middle?
Yes.
No, I wish I could do it. So we get a pendulum, it's in the middle, I just go, it's the power of my mind, and it goes whee like that. I can't do that. You'd be surprised how many physics books do that. All right, traditionally we start with displacement in the middle, okay? But we've got this slightly mad pendulum that starts in the middle. Quite a useful thing would be, in fact more useful than that, would be above the graph to draw where the pendulum is. Are you with me? So draw yourself a little pendulum above the graph so you're clear what's going on, okay? So here's the pendulum. It starts swinging for some reason that we don't quite understand. It just magically leaps into the air, okay? And it travels, obviously, to a point where it is... no, it's too far. It travels to a point where... it's gone right to that right-hand side, okay? Now, what do we call... I should have drawn this on the first one, really. What do we call the biggest distance it gets to? We've used that word once already. It's going to travel to, let's call that capital A. Right, and capital A, be careful with little a for acceleration, is the amplitude. All right. So if I've got a pendulum swinging like this, then its amplitude is that distance, or it's that distance in the opposite direction. All right. It's the biggest distance to the side the thing ever gets. Okay. So the maximum displacement, it's a good way to remember it. We call it the amplitude. So that's plus A. Down here will be minus A. So in simple terms, the pendulum swings between 0 in the middle, plus A, minus A, plus A, minus A, like that. Okay? So here we're at plus A, so that's going to be there. Yep. Where's it going after that?
Back down to the equilibrium.
That's it, it's coming back down to the equilibrium, isn't it? It's going to go back down to there. So let's do there. Yeah. Where's it going after that? It's going up the other side, isn't it? You with me? It's going the other way. Now it's all vector quantities, remember we're doing displacement, not distance, so it's going to have to be minus A, so we have to go down there. And after that it's going back to 0. Okay? So very important that you understand why each of those points is where it is. It's a bit wonky, my graph, but you get the idea. And the best way to do it is to draw yourself draw yourself a pendulum above it, all right? Pendulum in the middle, pendulum off to one side, pendulum in the middle, pendulum off to the other side, pendulum in the middle again, okay? And you should by now have drawn yourself a rather beautiful, rather wonky sine curve, okay? So what shape is the displacement graph? It's something to do with sine, okay? Right, so the thing we've learned today is that the displacement of an object doing SHM is a sine curve. Okay, we can get into the maths of how that looks as an equation a bit later on, but for the moment let's just see how that's linked to the velocity and the acceleration. Okay, doing equations with sine and cosine on a Friday morning is never a good idea. Okay. Now, while you're finishing off your lovely curve, what I'd like you to do is to think about where that's going to map onto on the next graph. Okay? Velocity is 0 in the middle, so that's 0 velocity in the middle of this graph. Up here would be V max, and down here would be minus V max. They haven't really got a special name, have they? This is just the fastest it goes, and this is just the fastest it goes the other way. Okay? In terms of distance, that's got a special name. The maximum displacement is called the amplitude, so that's plus A and minus A. Okay? Probably the easiest way to do this is to think about the zeros. If we're plotting this graph out in the same sort of way, whereabouts in the swing is the velocity 0? Think about it. When does the velocity equal 0? Imagine freezing the video. It's 0 there, because it's going from that way to that way. It's 0 there, because it's going from that way to that way. And in the middle, it's a maximum. So, I need to plot these points. The velocity is going to be 0 when it reaches the edges. That's right, isn't it? Yeah, when it reaches the edges, plus A, minus A, that's when the velocity is going to be 0. All right. If you could freeze frame it, it stops momentarily there, and comes hurtling through the middle at top speed. All right. So 0 velocity is going to be here and here. Are we agreed?
Yeah.
Yeah. Those are the points of maximum. Those are the points of 0 velocity. Those are the points where it stops. Okay. Tell me about the velocity at the beginning then. Well, it's going through 0, so it's going to be a maximum, isn't it? All right. Think of the 0. So these points here, that one, and that one. All right. Those 3 points are when it's passing through the equilibrium. And if you think about a pendulum, as it passes through the middle, it goes at top speed, doesn't it? Okay. Let me call that one there. Yeah. What do I plot here? It's going to have to be, yeah, because here, good way to draw this, perhaps put some arrows on. Here, it's passing through 0, travelling that way. Yeah. And I've chosen to call that V max positive, just because it is. When we get to here, which way is it going? Can you see? Imagine the swing. When it gets to this point, it's been out to that side and it's coming back, isn't it? All right. Can I convince you those 2 points there must have opposite signs on the velocity graph? All right. On the distance graph, they're both in the middle because they're both instants when it's in the middle of the swing. All right. But think about it. This point is that, and that point is that. Yeah. So this one, if you plot that, you could do it the other way around. You have this one as minus, that one as plus. But whatever you plot this one in terms of sign of its velocity, yeah, that one's going to go the other way. All right, because that is that, and that is that. Okay, and this one will be another one of those, won't it?
Yeah.
It's back up there. Happy? And if we draw that in, yeah, we get a rather rubbishy cosine curve. Right. Displacement for an SHM object, if displacement is like a sine curve, then velocity will be something like a cosine curve. Okay. Now, acceleration, various ways of doing this. If you do maths and calculus, you'll know each one of these is the gradient of the one before. That's one way of doing it. A nice way, I think, that's more physics than it is maths, is to remember that force is linked to, is to remember that acceleration is linked to force, all right? If you're trying to think about how something's accelerating, and you find that you can't work it out, think about the force acting on it, all right? If the force acting on an object is 0, what's its acceleration going to be?
0.
It's going to be 0, isn't it? All right? So this is Newton's second law of motion, basically, that force is linked to acceleration. Okay? So, what we need to think about, let's try and do the zeros first. Are there any places in the swing where the restoring force is 0? That's it. That's the definition of equilibrium, isn't it? The equilibrium position is it passes through the middle, that's the point where the tension and the weight balance out, and there is no restoring force. What keeps it moving through the middle is its own momentum, isn't it? If you stop the pendulum and put it at the equilibrium, it would just stay there, wouldn't it? Okay, so let's have a look at places where there is zero force. That's going to be the equilibrium points. So that's going to be there, that's going to be there, and that's going to be... There's 3 points straight away. When it's in the middle, there can't be any acceleration. What's the force pulling it back to the equilibrium when it's at the equilibrium? There isn't any, all right? You have to pull it slightly to the side to get a restoring force, okay? Now, let's have a look at this point here, okay? Here's the object, it's gone sailing through the equilibrium and it's out to there, okay? There is a restoring force acting on it, okay? Which way is the restoring force trying to pull the object? Back the other way, isn't it? All right. So think about it. If I displace the object this way, there's a force trying to pull it the other way, which is why this point has to be here. When it passes through the edge on that side, I'm drawing the restoring force as negative. Why am I doing that? Why am I plotting it as negative?
Because it's decelerating.
It's decelerating and then accelerating, isn't it?
It's opposite to the displacement.
That's it. In fact, remember our equation, F equals minus kx. There's displacement. Displacement isn't just a number, remember. Displacement is that graph. This is a constant with a minus sign. And this is the graph of force, which will be the same shape as the graph of acceleration. All right? Think about it. The answer to this question is really easy. It's something we did right at the start of the lesson. We said acceleration and force are equal to minus the displacement. Think about that sentence. Acceleration and force are minus the displacement. And I'm asking you what shape this graph is. Easy. It's minus the displacement. That doesn't mean turning 6 into minus 6. It means turning that graph into the minus version. All right. So remember, these two graphs are linked by a minus sign, aren't they? Yeah? Because the graph of acceleration will be the same shape as the graph of force, and that's the whole point of SHM, is force is proportional to minus displacement. So you don't actually need to think about it too hard. If you displace something that way, the force will be that way. So if this is the maximum displacement plus, we want the maximum force negative. Okay? This one has to be over here for the same reason. Got to be the opposite sign to that one. But actually it's very easy. You just want a graph which is the opposite shape. All right. So if that's a sine and that's a cosine, this is a
Minus sign.
This is a minus sign graph. The important thing to remember is these two graphs. People think, right, acceleration. Here's the pendulum. Now, where is it accelerating? It's easy. It's opposite of that one. All right. If this is SHM, then acceleration. Remember, acceleration is the same as the force graph. So put a thinks bubble there. Any area of physics, if you find thinking about what the acceleration is doing difficult, think about the force. Okay.